The universe has a way of keeping secrets, even when it seems to be speaking in plain sight. Imagine looking up at the night sky, tracing constellations and thinking that everything is still. Stars, frozen like tiny pinpricks in the dark. Yet, beneath that silence, everything is moving. Galaxies are sliding away from each other, not slowly but with a pace that seems to grow faster as time unfolds. It is as if space itself is stretching, carrying stars like lanterns drifting apart on a vast, invisible river. Scientists once believed this expansion should slow down as gravity pulls everything back together. Instead, the opposite is true. The fabric of the cosmos is accelerating as though pushed by some hidden hand. This mystery has puzzled astronomers for decades, giving rise to some of the most haunting questions of modern science. What force drives this relentless expansion? Why faster than expected? And what does it mean for the fate of everything we know? Tonight, as you drift into calm thought, let's wander gently through these questions. One step at a time, as though we are floating across the stars themselves. The mystery of a restless universe. When you hear the word universe, you might picture something grand, unshakable, eternal. But the truth is more surprising. The cosmos is not a still canvas. It is restless, alive in motion. Every galaxy is shifting, tugged and carried by forces we barely understand. To imagine this properly, think of a balloon being inflated. Each dot on its surface drifts away from the others, not because they move on their own, but because the balloon itself grows beneath them. Our universe behaves in much the same way. What makes this restlessness so mysterious is not simply that things move, but how they move. We expect expansion to follow a rhythm, like a firework bursting, slowing as sparks fade. Yet the universe shows no sign of slowing. Instead, it speeds up. Galaxies at the farthest reaches appear to flee faster and faster. This is not the behavior of something winding down, but of something pushing outward with determination. And it forces us to ask, what energy, what unseen breath fills the balloon of reality and keeps it swelling? It is here that science drifts into wonder, where mystery begins to outweigh certainty. You could stand beneath a quiet sky and never sense this hidden motion. Stars seem permanent, unmoving companions. Yet if we were to watch long enough, across millions of years, the constellations themselves would unravel, like patterns on water disturbed by an unseen current. The universe does not honor stillness. It insists on change, and this change carries everything outward. Our solar system, our Milky Way, even clusters of galaxies, all are passengers on this expanding tide, whether we feel it or not. That very inevitability gives the night sky a secret pulse. It is tempting to ask, why should this expansion matter to us? After all, galaxies beyond imagination are racing apart at distances so vast they will never return. But in their running lies the key to our cosmic story. The way the universe expands tells us what it is made of, how it began, and where it might end. To ignore this restless growth would be like trying to understand a beating heart while refusing to hear its rhythm. The mystery is not abstract, it is the rhythm of existence itself. As we lean closer into this enigma, we will see how humanity first noticed the subtle clues. At first, the stars seemed fixed, but careful eyes, guided by light itself, began to whisper another story. That is where our journey moves next, into the very first whispers of cosmic expansion. First, whispers of cosmic expansion. At the dawn of the 20th century, most astronomers held a simple belief: the universe was eternal and unchanging. Galaxies, if they were even recognized as such, were thought to sit still in a grand, endless space. But small details in the light of distant objects began to betray that illusion. When starlight was stretched into rainbows of color through glass prisms, something subtle appeared. The lines were shifted, nudged toward the red. These shifts were tiny whispers, almost dismissible, yet they suggested motion. Imagine hearing a faint echo in a vast canyon. It may not seem important at first, but if the echo repeats again and again, you begin to realize the canyon is alive with shape and sound. In the same way, these redshifts told astronomers that galaxies were not simply dots in the sky, but travelers. Light carried their motion across unimaginable distances. Each whisper of stretched light was a signal. I am moving away. And as more whispers were recorded, a pattern emerged. The universe itself seemed to hint at expansion long before anyone dared to say it aloud. For the astronomers of the time, this was unsettling. They were trained to see the heavens as stable, like a cathedral ceiling holding stars in perfect order. But these faint shifts spoke of dynamism, of motion beyond comprehension. One could ignore a single whisper, but not an orchestra of them. Galaxy after galaxy showed the same trait, their light sliding redward, as though space itself were stretching between us. The whispers turned into a chorus, one that could no longer be dismissed. It is important to notice how fragile such discoveries begin. No one set out to find an expanding universe. They sought to measure, to catalogue, to bring order to the chaos of stars. And yet in that order, a deeper chaos was revealed, a universe that refused stillness. The whispers did not give the full story, but they planted doubt in the assumption of permanence. Doubt is often the first step toward revelation. Here it was the first soft sign that the universe had secrets yet untold. Those whispers would not remain whispers for long. Soon a louder voice would rise, one that shattered old assumptions with undeniable clarity. That voice belonged to Edwin Hubble, whose discovery would forever change the way we think of our place in the cosmos. Hubble's astonishing discovery. Edwin Hubble was not the first to hear the whispers of expansion, but he was the one who proved they could not be ignored. Using the Mount Wilson Observatory, perched high above California, he peered deeper into the heavens than anyone before him. What he saw was breathtaking. Galaxies were not just scattered islands. Their speed of retreat grew larger the farther away they were. The pattern was undeniable. Like beads on a rubber band being stretched, the universe itself was expanding. Hubble's discovery was a moment of profound shock. Imagine believing your home was a still, solid ground, only to find it was a raft being pulled by an invisible tide. That is what his data revealed. The greater the distance of a galaxy, the faster it fled. This wasn't random. It was law-like, as though the universe had written its own rhythm. For the first time, humanity had proof that we lived in a cosmos not frozen in place, but swelling with time's passage. It was a discovery that pulled the rug from under centuries of certainty. What makes this so extraordinary is how simple the observation appears in hindsight. Measure the distance, measure the redshift, place the points on a graph, watch the line rise. And yet in that line lay the collapse of an entire worldview. The universe was not eternal in its current form. It had a beginning, and its expansion hinted at a story of origins. Suddenly, the night sky was not just a ceiling of stars, but a narrative in motion, a plot unfolding on the grandest stage imaginable. Hubble himself may not have grasped the full philosophical depth of his finding. He was cautious, a scientist presenting numbers. But the implication was staggering. If the universe is expanding, then rewinding the clock leads to a time when everything was closer, hotter, denser. This laid the groundwork for the idea of the Big Bang, though the term would come later. What mattered now was that we could no longer see the cosmos as a static cathedral. It was alive with expansion, and that truth would shape the next century of science. As the implications spread, more questions followed. If galaxies flee, how do we measure their pace? What tools allow us to chart this cosmic breath? To answer that, astronomers turned to the oldest messengers of all, light itself, stretched across the void into a cosmic ruler of time and distance. How galaxies slip further away. When you think of galaxies slipping away, you might imagine them flying through space like rockets. But the truth is stranger. Galaxies are not racing through emptiness. The space between them is expanding. It is as though you and I sat on a rubber sheet while it stretched. We would drift apart without moving our muscles. This distinction is crucial. The galaxies are mostly at rest in their local space, but that space itself grows, pulling them apart. It is motion, born not of engines, but of fabric, itself unfurling. This idea is not intuitive. Human minds are used to motion caused by forces, pushes, pulls, impacts. But the expansion of the universe is more subtle, more profound. It is the canvas itself stretching, carrying every brushstroke with it. When astronomers measure a galaxy's redshift, they are not recording its personal speed so much as the stretching of the intervening space. It is a reminder that in the cosmos, even the stage on which events unfold is not fixed. Space is dynamic, alive, willing to grow larger with time's passing. As galaxies slip further away, they reveal a pattern that deepens with distance. The farther they are, the faster they recede. This does not mean some galaxies are privileged or impatient. It is simply the geometry of expansion. On the surface of a balloon, dots farther apart are separated more quickly as the balloon grows. Scale itself accelerates the effect. The universe mirrors this geometry, a grand balloon where every cluster drifts away, with no center, no edge, just endless expansion in every direction. The poetry of this is striking. We are part of a universe where separation is inevitable, written into the fabric of time. Galaxies we now see will one day vanish from view, their light stretched beyond detectability. The universe slowly isolates us, not in malice, but in obedience to its own expansion. That reality is both humbling and haunting. To look at a distant galaxy is to glimpse a friend we may never see again, carried away by a tide we cannot resist. To measure and understand this slipping away, astronomers developed tools, or cosmic rulers, candles that shine with reliable brightness. They would use these markers to chart the distance, the pace, and ultimately the rate of expansion itself. It is here that the story turns to those guiding lights, Cepheids supernovae, and the flickers that became our cosmic yardsticks, the cosmic ruler of light. Light is our only bridge to the distant universe. Across darkness, across time, it carries whispers of where galaxies are, how fast they move, and what secrets they hold. But raw starlight is not enough. To measure distance, we need standard candles, objects whose brightness we can trust. This is where the cosmic ruler of light comes in. Certain stars and explosions shine with a predictable pattern, giving astronomers a yardstick to gauge distances otherwise unreachable. Without them, the expansion would be a ghostly rumor, unmeasurable and abstract. The most famous of these rulers are Cepheid variables, stars that pulse with rhythmic brightness. Like a cosmic heartbeat, their flicker tells us both how luminous they truly are and how far their light has traveled. Imagine hearing a drum in the distance. The volume tells you its closeness, but if you know how loud it beats by nature, you can calculate the exact distance. Cepheids beat steadily enough to serve as trusted guides, allowing us to chart galaxies like sailors charting stars across a restless sea. Then came supernovae, particularly type Ia explosions. These cosmic fireworks burn with such uniform brilliance that they too serve as beacons. When astronomers compared their apparent brightness to their expected brightness, they unlock distances across billions of light-years. Suddenly the map of the cosmos stretched further than imagination. And within that map, a shocking truth appeared. The expansion was not slowing, but accelerating. Light itself had carried this revelation to us, like a letter opened centuries late, its contents shaking everything we assumed. What makes these rulers so powerful is their universality. A Cepheid in one galaxy beats the same way as in another. A type Ia supernova explodes with the same brilliance, whether here or across the cosmic ocean. They are impartial witnesses, their voices consistent across time and space. To measure them is to borrow the universe's own clock and ruler, stitched into the fabric of starlight itself. These messengers gave astronomers confidence that their conclusions were not illusions, but truths whispered by the cosmos itself. And yet, as these rulers grew more precise, they unveiled contradictions. Different methods yielded slightly different expansion rates. The whispers of doubt returned, louder this time. Was the universe expanding faster than even these lights suggested? Or were we misreading the signals measuring distances across silence? The night sky is silent, but its silence is not empty. Light is the language it uses to speak across billions of years. To measure the scale of the universe, astronomers had to learn to translate this faint language into distance. How far away is a galaxy? How fast is it receding? These questions cannot be answered by rulers or tape measures, but only by decoding the faint fingerprints in light itself. Each shift, each color change, carries the story of distance, and with it, the tempo of expansion. When you hold a prism to sunlight, you see a rainbow. For astronomers, this rainbow is far more than color. It is a code. Dark lines appear within it, each one marking the identity of an element. Hydrogen, helium, oxygen. Each leaves its signature. When these signatures are displaced, when they slide toward red, they reveal that the source is moving away, and the amount of shift tells us how fast. It is astonishing that something so quiet, so fragile, could carry across billions of light-years a precise message of speed. But distance requires more than velocity. To know how far a galaxy truly is, astronomers relied on brightness as a guide. If we know how luminous a star ought to be, we can compare it to how luminous it looks. The dimming of light, stretched and weakened by distance, becomes the ruler itself. It is a soft ruler, subject to dust, distortions, and uncertainty. Yet it is the only one available in the silence of space. It is remarkable to think that from mere photons entire scales of the cosmos are drawn. The patience required for this work cannot be overstated. To measure distances across silence means to spend years gathering light that left its source long before human civilization began. Every telescope becomes a time machine, every observation a reaching hand into prehistory. And the more carefully astronomers measured, the clearer it became. The universe was not just expanding, it was expanding at a rate that defied expectations. This silence was speaking louder than ever, demanding we listen more closely. And so the silence gave way to rhythm. Cepheids pulsed, supernovae flared, galaxies whispered redshift. Together they sang of expansion. And from this song emerged the first clear measurement of how fast the universe was stretching, a number that would later be known as the Hubble constant. But before diving into the constant, the story must touch the stars that guided the way, the flickering beacons called Cepheids. Flickering beacons called Cepheids. Among the vast sea of stars, Cepheid variables shine with a peculiar gift. They do not keep steady brightness. Instead, they pulse, growing brighter and dimmer in regular cycles. These flickers are not random. They follow a rule. The longer the period of their pulse, the more luminous the star truly is. This simple relationship transformed Cepheids into cosmic beacons, candles that could illuminate distances far beyond the reach of parallax or simple geometry. Henrietta Swan Leavitt, a woman working quietly at Harvard in the early 1900s, was the one who uncovered this hidden pattern. She compared Cepheids in the Magellanic Clouds and noticed the strict correlation between their brightness and pulsation period. Her discovery was revolutionary. With it, astronomers could measure distances to galaxies far beyond the Milky Way. Leavitt's law became the first stepping stone toward cosmic expansion. A quiet flicker in distant stars became the foundation for measuring the universe itself. To imagine their role, picture walking across a dark plain with only flickering lanterns in the distance. If you knew how bright those lanterns were meant to be, their apparent faintness would tell you exactly how far you had wandered. Cepheids served in this way. Lanterns strung across the night sky, allowing astronomers to trace the path of galaxies slipping away into the dark. Without them, Hubble could never have confirmed expansion, nor could modern astronomers refine the cosmic ruler of light. But even Cepheids carry challenges. Dust dims their light unevenly. Some galaxies hold them in crowded regions where starlight overlaps. Precision is difficult, yet still, the rhythm of their flicker speaks clearly enough. Their loyalty as guides has stood for a century, their cycles unchanged, their message reliable. In their steadiness, astronomers found comfort, and yet in their measurements they also found the first hints of contradiction, of rates of expansion that refused to align neatly with other methods. It is remarkable that stars beating like slow, cosmic drums could reveal something so vast. From their flickers came the first true map of the universe's restless heart. But Cepheids alone were not enough. Astronomers needed a brighter, more dramatic candle, one capable of reaching even further. That candle was found in the furious brilliance of supernovae, the cosmic lighthouses that briefly outshine entire galaxies. Supernovae as cosmic lighthouses. When a star ends in explosion, it becomes a supernova, an event of astonishing brightness. Among these, type Ia supernovae stand apart. They occur when a white dwarf star steals matter from a companion until it reaches a critical mass, triggering a runaway reaction. The explosion always ignites at the same threshold, meaning these supernovae shine with near-uniform brilliance. That uniformity makes them perfect cosmic lighthouses. Astronomers could spot them across billions of light-years, comparing their apparent brightness to the expected standard to measure vast distances. The beauty of these lighthouses is not just their intensity, but their predictability. For a brief time, they rival the luminosity of an entire galaxy, visible across the cosmos. They flare and fade in a pattern so consistent that astronomers can trust them as universal yardsticks. If Cepheids are lanterns along the roadside, supernovae are bonfires on distant hills, blazing clear markers of how far the path stretches. They extend our measuring stick to the deepest cosmic neighborhoods, offering clarity where faint whispers alone cannot reach. And it was through these lighthouses that one of the greatest surprises of modern astronomy was uncovered. In the late 1990s, two teams working independently measured distant type Ia supernovae. To their shock, the data showed galaxies were not slowing down in their retreat. Instead, they were accelerating. The universe was not only expanding, it was expanding faster and faster. A discovery so startling it would eventually earn the Nobel Prize. Supernovae had turned from simple distance markers into heralds of an entirely new cosmic force. The implications were staggering. For centuries, gravity was assumed to be the dominant player, the brake that should slow expansion. Yet these lighthouses revealed a universe accelerating as though pushed by an unseen hand. To explain it, astronomers invoked the concept of dark energy, or mysterious force permeating the vacuum driving galaxies apart. Without the cosmic lighthouses, this revelation would have remained hidden. It was the explosions of dying stars that lit the truth of the restless universe. And so the story deepened. Cepheids gave us the first steps. Supernovae extended the road, and together they led us to the unsettling realization that the expansion was not behaving as expected. The first hints of acceleration had been seen, and the puzzle of the universe had grown stranger. Yet, as these lighthouses blazed, contradictions in the measurements began to appear, small differences that would grow into a tension no one could ignore. The first hints of a faster universe. Long before the word dark energy was spoken, astronomers noticed peculiar inconsistencies in their data. Some galaxies seemed farther than expected for their redshift, others closer. The ruler of light did not always agree with the map of expansion. At first, these were brushed off as errors, perhaps dust, miscalibration, or statistical noise. But as the data grew, the whispers turned into patterns. The expansion was not only present. In certain measurements, it appeared faster than what theory predicted. This was deeply unsettling. Theoretical models based on general relativity and the known contents of the universe suggested that expansion should slow down. Gravity, after all, is attractive, and the combined mass of stars, gas, and dark matter should have been enough to gradually rein in the stretching of space. Yet, here were signals suggesting the opposite. The cosmic balloon was not deflating or holding steady. It was swelling more vigorously, as though filled with a new breath of unseen energy. Some resisted the idea, preferring to search for errors in measurement. After all, the consequences of a faster universe were profound. If true, it meant there were forces at play that physics had not accounted for. Something beyond matter, beyond light, beyond the familiar. For a community built on precision and prediction, such an unknown was a disruption, and yet the hints refused to vanish no matter how carefully telescopes recalibrated their eyes. The hints grew louder with each new observation. Galaxies at the edge of detection were racing away more quickly than those nearby, their redshifts stretching further than anticipated. It was as if the universe itself was telling a story too bold to believe. Astronomers could no longer hide behind margins of error. The faster universe was not an illusion, it was reality, and reality was outpacing expectation. That realization planted the seeds of one of the greatest mysteries in cosmology. These hints, fragile at first, became undeniable when confirmed by the supernovae surveys of the 1990s. What was once whisper became proclamation. The universe was accelerating, but acceleration demanded explanation. An explanation required confronting the possibility of something entirely new. A puzzle that deepened into one of the most important debates in modern science. What do we call this force, and how do we measure it? When numbers didn't agree, science thrives on agreement. When different methods yield the same result, confidence grows. But in measuring the universe's expansion, numbers refused to align. Cepheids gave one value for the Hubble constant. Supernovae supported it, but the cosmic microwave background, a baby picture of the universe taken 380,000 years after the Big Bang, gave another, slightly lower value. These differences, once small, sharpened with precision. The disagreement became impossible to ignore. The universe was telling two stories, and no one knew which to trust. This tension is now famously called the Hubble tension. On one side stand the local measurements based on Cepheids and supernovae, pointing to a faster expansion rate. On the other, the early universe measurements derived from the cosmic microwave background, suggesting slower growth. Both methods are rigorous, both backed by years of data, and yet their results diverge like two rivers that should meet but never quite touch. It is as though the universe is playing a double game, leaving scientists puzzled and humbled. The implications are profound. If the numbers differ, then either hidden errors lurk in our instruments or, more tantalizingly, our understanding of physics is incomplete. Perhaps new particles influence the early universe. Perhaps dark energy behaves differently across time. Or perhaps space itself has properties we do not yet imagine. Each possibility carries both excitement and unease, for in every case it means reality is stranger than the models we built to contain it. Astronomers gather in conferences, presenting their cases, defending their numbers. Entire careers are devoted to refining a single measurement, and still the tension persists. The numbers refuse harmony. The more precise the instruments, the sharper the divide. It is as though the universe delights in testing human patience, dangling certainty just out of reach. Some find this frustrating, others find it beautiful. A reminder that discovery is not a destination, but a process that never truly ends. And so we are left in a place of wonder. The numbers do not agree, yet both might be right in their own way. Perhaps we are glimpsing a universe in transition, a cosmos whose expansion shifts character across epochs. Or perhaps we are still too young, too early in our science to comprehend the deeper forces at play. A puzzle in the cosmic clock. When scientists first set out to measure the expansion rate, they expected the universe to behave like a clock, steady, predictable, each tick aligned with the laws of physics we knew. But as data accumulated, the clock began to look broken. Different hands pointed to different hours. One clock told us the universe was older, another whispered it was younger. Each tick of light, each flicker from galaxies, seemed to follow its own tempo, leaving us with a puzzle carved directly into the flow of time itself. This puzzle is not just academic. If the universe is younger or older than we think, it changes everything about our cosmic story. It reshapes our timeline of galaxy formation, star birth, and even the emergence of life itself. Imagine trying to trace your family tree but finding that every record gives a different birth year. Which version is true? The puzzle of the cosmic clock strikes at that same sense of identity. Not for one family, but for all existence. The more carefully we listened, the more contradictory the ticking became. At the heart of this puzzle lies the Hubble constant, the number that tells us how fast the universe expands at present. It should be simple: count distances, track redshifts, and measure the slope of expansion. But simplicity never survives long in the cosmos. Depending on how you measure, the number changes. Local methods whisper a faster pace, while early universe methods murmur a slower one. The cosmic clock refuses to settle, as if two different timekeepers are pulling their hands apart. For astronomers, it is maddening and marvelous all at once. And yet, there is beauty in this disagreement. A puzzle in the cosmic clock is not a failure, but an invitation. Nature hides its secrets in the gaps between numbers, in the places where certainty collapses into confusion. That is where discovery blooms. Each mismatch in the cosmic clock is a doorway to a new possibility of hidden physics, unseen particles, or forces we have not named. The universe, restless as ever, tempts us to follow its contradictions deeper into mystery. And so the puzzle became a debate, an argument carved across galaxies and epochs. Astronomers realized they were not only measuring expansion, they were measuring their own assumptions about reality. Ahead in this journey, we step closer to that constant, the Hubble constant itself, and the storm of disagreement it has unleashed. The Hubble constant debate. The Hubble constant is one of the most important numbers in science. It tells us how quickly the universe is expanding right now. Yet this number has become a battleground. Different groups of astronomers using different methods arrive at different answers. Some claim the constant is around 73 kilometers per second per megaparsec. Others, studying the early universe, say it is closer to 67. A difference of just a few units may seem small, but in cosmology it is enormous, a rift wide enough to demand an explanation. The debate often feels like watching two clocks ticking at slightly different speeds. Both are built carefully, both are trusted, and yet their rhythms refuse to match. If one is correct, the other must be flawed. But what if neither is wrong? What if the universe itself is shifting, changing its tempo across time? This possibility transforms the debate from mere disagreement into a clue. It suggests that perhaps our physics is missing a note, like a song played without its final chord. The tension may not be an error at all, but a revelation. What makes this debate so fascinating is the passion it inspires. Teams of scientists spend years refining measurements, checking dust corrections, recalibrating instruments, and publishing results, only to find that the disagreement remains. Conferences echo with arguments, papers spark rebuttals, and still the tension holds. It is as though the universe is determined to keep its secret, revealing just enough to stir the mind, but never enough to settle it. This debate has become one of the defining questions of modern astronomy. Beyond the numbers lies a deeper philosophical unease. If the universe defies our calculations, what does that say about our models? Are we arrogant to believe we understand its rhythm? Or are we on the verge of discovering something profound? A hidden layer of reality that alters how time and expansion truly work? The debate is not only about precision, it is about humility before a cosmos that may be far stranger than our mathematics can grasp. And that humility is a rare, necessary gift. Still, scientists press on. They cannot resist the lure of a constant that refuses constancy. Each new measurement, each fresh data set is another attempt to pierce the mystery. And as the debate intensifies, the story deepens. The question is no longer just about numbers, it is about methods, two very different ways of measuring expansion. Local galaxies tell one story, the early universe tells another. And in their tension lies the riddle of existence itself. Two ways of measuring time's stretch. To understand why the debate endures, you must see how expansion is measured from two perspectives. One method looks close at nearby galaxies, using Cepheids and supernovae as rulers. This local method measures the universe as it is today, in the here and now. The other method looks far back, at the afterglow of the Big Bang, the cosmic microwave background. This early method uses physics and models to predict what the expansion rate should be today, based on ancient conditions. Both are valid, yet they diverge like two storytellers describing the same journey from opposite ends. The local approach feels grounded, almost intuitive. You measure a distance, compare brightness, track redshift, and plot the numbers. It is the work of patient observation, a slow tally of light that reaches us across time. The early approach, by contrast, is deeply theoretical. It takes a snapshot of the infant universe, applies equations of cosmology, and runs the clock forward. The difference is like measuring a tree's height today versus predicting it from the seed's first sprout. Both methods aim for the same truth, but they travel very different roads. The stretch of time is at the core of this divide. Local methods show a faster expansion, as if the tree grew quicker than expected. Early methods show a slower one, as if the seed's growth had been steady all along. Reconciling the two is not easy. If the universe accelerated somewhere in between, it means forces unknown may have shaped its growth. Dark energy, new particles, or shifting laws of physics could all be responsible. The very act of measuring time's stretch reveals gaps in our understanding of time itself. What fascinates many is that both methods are incredibly precise. These are not sloppy numbers. They are razor-sharp, honed by decades of refinement. And yet, the precision only sharpens the conflict. The more carefully astronomers measure, the more stubborn the disagreement becomes. It is like tuning two instruments to perfection, only to discover they play in slightly different keys. The dissonance becomes haunting, as though the universe is telling us there is a missing harmony we have not yet heard. And so two ways of measuring time's stretch continue to shape the debate. Neither can be dismissed, neither can be declared the winner. Each holds part of the truth, and each deepens the mystery. As we move further, we will see how even the galaxies around us seem to take sides, some whispering of a faster universe, others of a slower one. The very fabric of the cosmos seems to speak in contradictions, daring us to listen closer. Local galaxies telling one story. Look around our cosmic neighborhood, and you will find galaxies whispering of urgency. Cepheids in nearby galaxies, supernovae flaring in clusters not far from us, all point to a faster pace of expansion. The numbers they reveal hover around 73 kilometers per second per megaparsec. This suggests that every megaparsec of distance adds 73 kilometers per second of recession speed. It is as though the universe is racing ahead, unwilling to slow down, each local galaxy adding its voice to the chorus of acceleration. This story has weight because it is based on direct observation. We are not predicting from the past, we are listening to the present. Light from galaxies, near enough to be measured with trusted rulers, tells us what is happening right now. There is a certain intimacy in these measurements, a sense that we are taking the universe's pulse in the moment, not inferring it from ancient echoes. And the pulse is quick. The heartbeat of expansion is faster than theory predicted. Local galaxies sing of a restless cosmos, one that runs ahead of expectation. Yet, as compelling as this story is, it carries uncertainty. Dust clouds obscure light, distortions twist brightness, and calibration is never perfect. Astronomers know this, and they work tirelessly to correct for it. But even after corrections, the message persists: a faster universe. The stubbornness of this result forces us to take it seriously. It is not a fleeting illusion. It is a story written across dozens of galaxies, across countless flickering cepheids and blazing supernovae, all agreeing on the same tempo. The emotional weight of this cannot be ignored. Imagine spending decades trusting the universe to follow a script, only to discover it improvises instead. The galaxies near us have betrayed the neatness of our equations, and in their betrayal lies the seed of discovery. If they are right, then something extraordinary is happening. Something unseen accelerates the cosmos today, something our physics must reckon with. The galaxies may not know it, but they are messengers of revolution, voices calling us to rethink reality itself. But while local galaxies tell one story, the early universe tells another. It whispers of a calmer pace, a slower rhythm, a steadiness that contradicts the local urgency. Between these two voices lies the heart of the Hubble tension, and with it, the possibility of an entirely new chapter in cosmology. The early universe telling another. If local galaxies sing of acceleration, the early universe hums a different tune. The cosmic microwave background and the faint afterglow of the Big Bang offers a snapshot of the cosmos when it was just 380,000 years old. This ancient light, mapped with exquisite detail by satellites like WMAP and Planck, reveals a universe structured by simple physics. From its patterns, we can predict today's expansion rate, and the prediction is slower, around 67 kilometers per second per megaparsec. A calmer, steadier growth than local galaxies suggest. This slower rate is not arbitrary. It emerges from a model of the universe that fits countless observations. The balance of matter, radiation, and dark energy, the geometry of space, the birth of structure itself. It is a model that has passed test after test, a framework that describes not just expansion, but the entire history of cosmic evolution. To doubt it is to doubt the very foundation of modern cosmology, and yet the disagreement with local galaxies lingers, growing sharper with every refinement. Two versions of truth sit side by side, demanding reconciliation. The early universe, in its whisper of calm, carries authority. Its voice comes from a time when conditions were simpler, when the cosmos was a nearly uniform soup of particles and light. To measure it is to measure the most pristine state of existence we can access. That clarity is why many astronomers lean toward trusting it. If the present disagrees with the past, perhaps it is the present that is misunderstood. Or perhaps, and here lies the intrigue, something new intervened between then and now, altering the expansion in ways our models do not yet capture. The tension between these two voices is haunting. It is like reading two chapters of the same book, only to find they describe different endings. Both are written clearly, both are consistent within themselves, but they cannot be reconciled. Something is missing. A hidden passage, a secret note. This missing piece is where the greatest discoveries of the future may lie. For in the dissonance of the early and local measurements, the universe is hinting at truths not yet named. And so we arrive at the center of the cosmic debate. Local galaxies cry faster. The early universe insists slower. Between them, the Hubble tension grows, daring us to choose or perhaps to imagine something beyond both. A cosmic tension grows louder. What began as a small disagreement has now become one of the loudest puzzles in modern science. Astronomers can no longer ignore it. The Hubble tension is not fading with time. It is growing sharper, like a note that won't resolve in a song. Every new telescope, every new data set, seems only to reinforce the divide. The more carefully we measure, the louder the cosmic contradiction becomes. It feels almost as if the universe is deliberately whispering a riddle, daring us to confront truths we do not yet see. For scientists, tension is both frustrating and irresistible. It means something is being missed. When numbers refuse to agree, nature is leaving clues scattered across the stars. The louder this tension grows, the more it calls us to search beyond familiar ideas. It forces humility. Perhaps the universe is not bound by the tidy equations we've written. Perhaps reality itself is richer, stranger, more layered than the physics we know. The tension is no longer a technical problem. It is a doorway, and doorways are always invitations to step through. It is tempting to look for mistakes in the instruments. After all, human tools are imperfect. Dust in the telescope, biases in the calibration, errors in the analysis, these are all reasonable suspects. But the persistence of the tension makes such explanations less convincing. We correct for dust, refine our calibrations, double-check our equations, and still the discrepancy remains. Like a shadow that does not vanish no matter how you shift the light, the tension clings. It is not an illusion, it is something deeper. This persistence has changed the tone of the conversation. What was once seen as an error is now considered evidence. If the cosmic clock ticks differently depending on how you measure it, then perhaps there is no single constant at all. Perhaps expansion itself has changed over time. Perhaps the energy driving it has shifted character across cosmic history. These are not casual ideas. They are radical, reshaping the very framework of cosmology. And yet they are now taken seriously because the tension demands it. The louder the tension grows, the more it points toward mystery. And in that mystery, a new force begins to emerge. One that would become the most haunting player in this story. Dark energy. To speak of it is to speak of the vacuum itself, a presence, invisible yet powerful, filling space with a push that accelerates the expansion of all things. Could hidden physics be speaking? What if the tension is not an error but a voice? a quiet signal from hidden physics speaking through the numbers. The universe may be telling us that our models are incomplete, that the rules we assume are fixed are only part of the story. Imagine listening to a song on a cracked radio. You hear the melody, but beneath it, faint distortions ripple. The distortions are not mistakes. They are evidence of layers beyond what the radio can play. The Hubble tension may be that same distortion whispering of hidden physics. Some suggest the presence of particles yet undiscovered, light, elusive beings that interact weakly, shaping the early cosmos. Others hint at interactions between dark matter and dark energy, unseen forces weaving together in ways we cannot yet detect. There are even proposals that space and time themselves may not behave as we assume, that constants may evolve, that the very fabric of reality is dynamic. These ideas sound speculative, but speculation is often the soil where revolutions begin. Each possibility is a reminder that the cosmos might be stranger than our boldest guesses. The beauty of science is that it takes whispers seriously. It does not dismiss the improbable simply because it is uncomfortable. When hidden physics speaks, the language is faint, encoded in contradictions and anomalies. To hear it, we must train ourselves to listen, and listening requires patience, humility, and imagination. The Hubble tension, then, is not just a number, it is a call to stretch the imagination as wide as the universe itself. It is an echo from reality's deeper layers, inviting us to translate its meaning. Some may find this unnerving. If the rules of physics are incomplete, then everything we've built on them must be re-examined. But history reminds us that every great leap in science was born of such unease. Gravity itself was once a mystery, as was electromagnetism, as was quantum physics. Each time, hidden physics spoke softly until we were ready to listen. Now the universe may be speaking again through expansion, through tension, through the restless clock of the cosmos. And what it speaks of most clearly is a force beyond all else, a presence not tied to matter, not tied to light, but to the vacuum itself. This presence has been named dark energy, and it has become the leading candidate for the hand that pushes the universe faster than expected. Dark energy enters the stage. Dark energy. The very phrase feels ghostly, a name for something we cannot see, cannot touch, and yet believe to be real. It emerged from necessity, from the shocking realization in the 1990s that the universe's expansion was accelerating. If galaxies speed away, there must be a force pushing them. Not gravity, which pulls inward, but something opposite, a force that drives outward. This force was named dark energy, not because we understand it, but because it fills the unknown with a placeholder. It is the most powerful yet mysterious actor in the cosmic play. The idea is staggering. 70% of the universe's energy is this unseen entity. More than stars, more than galaxies, more than all visible matter combined, dark energy dominates the cosmos, and yet we know almost nothing about it. It does not shine, it does not cluster, it does not interact in any way we can measure, except through expansion. It is like a breath across the void, invisible but undeniable, shifting the pace of reality itself. To accept dark energy is to accept that the majority of existence lies hidden beyond perception. But perhaps what makes dark energy most unsettling is its constancy. It does not fade as the universe expands. It remains. In fact, the more space stretches, the more dark energy there is because it fills the vacuum itself. Imagine inflating a balloon and finding that the air grows denser as the balloon grows larger. That is the strange, haunting property of dark energy. It ensures acceleration will not end. Expansion will only grow faster, carrying galaxies ever further apart until the night sky grows lonelier with time. The mystery is profound. What is dark energy? A property of the vacuum, a field that permeates space, a sign of dimensions unseen? Each hypothesis opens a door, and each door reveals more questions than answers. And yet its existence is the simplest explanation for the restless universe we observe. Without it, acceleration cannot be explained. With it, the riddle deepens, for how can something so dominant remain so hidden, so silent, so untouchable? It is as if the universe insists on reminding us of how little we know. And so dark energy takes the stage as the silent ruler of the cosmos. But it is not alone. To truly understand expansion, we must also consider its quiet companion, dark matter, the invisible weight that shapes the cosmic web. Where dark energy pushes outward, dark matter holds together. Together they write the balance of expansion, a dance between unseen opposites across the stars. The vacuum that pushes apart. It is almost poetic to think that the emptiest thing we know, i.e. the vacuum, might be the very source of cosmic acceleration. We imagine emptiness as nothingness, a hollow without substance. Yet quantum physics tells us the vacuum is restless, filled with fluctuations, fields, and virtual particles flickering in and out of existence. In this jittering sea perhaps lies the energy that drives expansion. If so, then nothingness is not empty at all. It is alive, it is potent, and it pushes galaxies apart as if space itself carries its own fuel. This idea is not new. Einstein once inserted a cosmological constant into his equations to keep the universe static, a term that acted like a repulsive force in the fabric of space-time. He later called it his greatest mistake. And yet, in light of acceleration, the cosmological constant has returned as a prime explanation for dark energy. Perhaps Einstein was right after all, not about a static universe, but about the vacuum's ability to push. The constant may be the signature of the vacuum itself, a quiet pressure that has shaped the universe since its birth. The thought is haunting. Every cubic centimeter of space, no matter how empty, may carry energy. And because space expands, that energy multiplies. The more space there is, the more vacuum energy exists, and the stronger its push becomes. This feedback loop ensures that expansion not only continues but accelerates. It is a runaway process written into the nature of reality. The universe does not need external fuel. Its own emptiness is enough to drive its acceleration endlessly forward. But there is a puzzle here. When physicists calculate the vacuum's energy using quantum theory, the number they arrive at is outrageously larger than what observations suggest. So large, in fact, that if it were true, the universe would have ripped apart long ago. The fact that we are here at all suggests the vacuum's push is real, but far subtler than theory predicts. This mismatch between theory and observation is one of the greatest unsolved problems in physics. The vacuum pushes, but it pushes with a delicacy we do not yet understand. And so we are left marveling at the irony. The nothingness we once dismissed as empty may hold the key to everything. The vacuum, invisible and silent, may be the hidden engine of cosmic acceleration. But expansion is not only shaped by the push of emptiness, it is also shaped by the weight of what is hidden, the unseen matter that binds galaxies together and resists the pull of separation. To explore the restless universe, we must turn to that invisible weight, dark matter. A gentle force with unstoppable will. Dark energy is often described as gentle. Its effect on any small scale is imperceptible. It does not tear apart solar systems, nor does it pull stars from their orbits. You and I feel nothing of it as we move through our days. Yet across the cosmos, its will is unstoppable. Over billions of years, this gentle push has reshaped the fate of galaxies, accelerating them apart at speeds that no gravity can reverse. It is proof that strength does not always roar. Sometimes it whispers steadily until the universe itself bends. This quietness is deceptive because it does not act violently. It is easy to overlook. but its persistence is what makes it formidable. Every moment, every second, the expansion grows faster, galaxies drift further, light stretches thinner. No force we know can counterbalance it. Gravity binds locally, keeping planets around stars, stars in galaxies. But on the grand scale, dark energy wins. Its victory is written into the accelerating graphs of expansion, into the disappearing galaxies we may one day lose sight of forever. Gentle, yes, but unstoppable all the same. Philosophically, there is something haunting here. A force we cannot see, cannot touch, dictates the destiny of everything. Stars will fade, galaxies will drift, and one day the night sky itself may grow empty, not because of destruction, but because of separation. This is the ultimate irony of dark energy. It does not destroy by breaking, but by pushing. It is a force of absence, making space so vast that even light cannot bridge the gaps. Its victory is quiet, but absolute. For many, this picture is melancholic. To imagine a future where the universe grows colder, lonelier, and darker is unsettling. And yet, there is also beauty in it. Beauty in the idea that something so delicate, so silent, can guide the larger structures of existence. Beauty in the reminder that strength does not need noise. The universe, restless and expansive, is guided by whispers more than shouts. And in those whispers, we see the poetry of reality itself. And so as we follow this story, we see two hidden players, dark matter and dark energy, shaping the fate of expansion. One holds together, the other pushes apart. Together they define the balance of the cosmos, the weight of invisible matter. If dark energy pushes outward, then something must also pull inward. That pull comes from dark matter, invisible, yet heavy beyond imagination. Unlike ordinary matter, it does not shine or emit radiation. We cannot see it directly, but we know it exists because galaxies spin too fast to be held together by visible stars alone. Without this hidden weight, galaxies would fly apart like sparks from a fire. Dark matter is the invisible glue of the cosmos, binding structure against the restless tide of expansion. The evidence is everywhere once you know how to look. Stars at the edges of galaxies orbit too quickly, as though pulled by an unseen hand. Clusters of galaxies bend the light of objects behind them, a phenomenon called gravitational lensing. These bends reveal more mass than what we see. That extra mass is dark matter. It outweighs visible matter by a factor of 5. For every ounce of stars, planets, and people, there are 5 ounces of this unseen substance, shaping the grand design silently from the shadows. Dark matter does not resist expansion the way dark energy accelerates it. Instead, it provides the scaffolding on which galaxies form. Imagine a spider's web strung across emptiness. Dust settles into the threads forming patterns. In the same way, dark matter's gravity pulls gas and stars into the vast web of the universe. Without it, there would be no galaxies, no clusters, no cosmic architecture. The universe would be a diffuse mist, never coalescing into the shapes we now see when we look through telescopes. And yet, dark matter itself remains nameless. We do not know its nature. It could be exotic particles beyond the standard model of physics. It could be primordial black holes hidden in darkness. It could even be something we have not yet imagined. What matters for our story is this: without dark matter's weight, expansion would erase structure. It is the quiet counterbalance to the universe's restless flight. Expansion pushes, but dark matter anchors, giving form to the galaxies that drift apart nonetheless. So we see the cosmos as a balance of opposites, dark matter binding, dark energy pushing. But to trace how this balance unfolded, we must go back to the very beginning, to the echoes of the Big Bang itself. when the seeds of expansion were first sown into the fabric of space. Dark matter shaping the dance. Picture the universe as a grand ballroom. Dark energy is the force pulling dancers apart, while dark matter is the hand guiding them into formation. Without dark matter, the cosmic dance would scatter into chaos. Its gravity provides the stage, holding galaxies in clusters, weaving filaments that stretch across billions of light years. This dance is not one of harmony alone. It is a contest, a tug-of-war between the inward pull of dark matter and the outward push of dark energy, a contest that defines the pace of cosmic expansion. Observations of the large-scale structure reveal this beautifully. Galaxies are not sprinkled randomly across the sky. They form webs, filaments, nodes, and voids. These patterns mirror computer simulations where dark matter is the invisible scaffolding. As space expands, galaxies cling to this web, resisting separation for a time. Yet, over billions of years, dark energy gains the upper hand, stretching the filaments, widening the voids, thinning the web. The dance becomes less intimate, more distant, as expansion accelerates. The ballroom grows larger, but the dancers drift apart. This shaping is visible in gravitational lensing surveys. When astronomers map the distortions of distant light, they see not random scatter, but vast, coherent structures shaped by dark matter's pull. It is astonishing to think that by watching light bend, we can sketch an invisible skeleton of the universe itself. Dark matter is silent, but its fingerprints are everywhere, in the shapes of galaxies, in the arcs of lensed light, in the patterns of the cosmic web that stretches farther than imagination. Yet even as dark matter binds, it cannot resist forever. Dark energy is patient. With time, its push dominates, the balance shifts. Clusters loosen, filaments thin, galaxies recede. The dance is not one of eternal embrace, but of slow separation. This inevitability is written into the equations and observed in the sky. It is not a tragedy, but a natural rhythm, the universe unfolding its story as it must, with dark matter and dark energy shaping its steps along the way. To truly understand this dance, we must listen to the oldest song of all, the faint afterglow of creation. The cosmic microwave background carries the memory of how matter, both dark and visible, shaped the infant universe. It is a map not only of what was, but of how expansion began. Why gravity alone is not enough. For centuries, gravity was the universal answer. From apples falling to planets orbiting, gravity explained motion with elegance. It was tempting to believe gravity alone could explain the universe's expansion. After all, if everything pulls on everything else, then expansion should slow, naturally, like a ball thrown upward falling back down. But as data grew, it became undeniable. Gravity alone is not enough. It binds locally, but on cosmic scales, another force reigns, one that drives acceleration rather than halts it. The failure of gravity here is not weakness, but limitation. Gravity explains why stars gather, why galaxies spin, why planets remain loyal to their suns, but it cannot explain why galaxies recede faster than expected, nor why the expansion accelerates. For that we need something opposite, a push, not a pull. This realization reshaped cosmology. It meant that the universe is not governed by one force alone, but by a delicate interplay of opposites, gravity binding, dark energy expanding, dark matter stabilizing in between. The universe is not simple, it is a balance of contradictions. Some theorists have asked, could gravity itself be modified? Could it behave differently at vast scales, weakening or changing character? This idea, known as modified gravity, is a serious contender. Perhaps Newton and Einstein gave us part of the truth, but not the whole. If gravity bends differently across billions of light years, then expansion's acceleration might be explained without invoking dark energy. But such models face challenges, for they must also explain the success of Einstein's equations everywhere else. The jury is still out. What remains clear is that expansion is not the passive result of gravity's decline. It is the active result of something else, something that pushes outward. And so gravity must share the stage. Its role is undeniable, but incomplete. It sculpts galaxies, binds clusters, bends light, yet it bows before the acceleration of the cosmos. The lesson is humbling. Even our oldest, most trusted law must accept its limits in the face of a restless universe. To hear this lesson most clearly, we look to the earliest chapters of cosmic history. There, in the afterglow of the Big Bang, we find the echoes of a universe too young for complexity, too raw for illusion. The cosmic microwave background is the closest thing we have to a baby picture of the universe. And in that picture, expansion's first secrets are written, echoes of the Big Bang. Imagine standing in a silent forest, hearing a faint hum that has been there since the dawn of time. That is what the cosmic microwave background, CMB, is. The afterglow of the Big Bang, a soft radiation bathing the universe. Discovered in 1965 by accident, it is the oldest light we can see, released when the cosmos was just 380,000 years old. Before that, the universe was too hot and dense for light to travel freely. But when it cooled, light broke free, filling space with a glow that has traveled ever since. The CMB is astonishingly uniform, the same in every direction to 1 part in 100,000. And yet those tiny fluctuations, slight ripples in temperature, contain the seeds of all structure. They show where matter was a little denser, where gravity would later form galaxies. They also reveal the universe's geometry, density, and rate of expansion in its infancy. This ancient echo is a treasure chest of information, one that scientists have opened with satellites like COBE, WMAP, and Planck. Each map revealed the universe's earliest story in finer detail. From the CMB, we learn that the universe began hot, dense, and rapidly expanding. The patterns of its ripples confirm the presence of dark matter and suggest the dominance of dark energy in the future. They also allow precise predictions of the Hubble constant, but these predictions disagree with today's local measurements. Thus, even the universe's baby picture deepens the puzzle. It is as if a photograph of a child predicts an adult of a certain height, only for the grown adult to measure taller than expected. The echoes of the Big Bang are humbling. They remind us that the universe has memory, that light itself carries a record of its earliest days. To study the CMB is to look not just across space, but across time, into the first moments when structure emerged from chaos. The fact that we can detect this faint glow with radio dishes on Earth speaks to the quiet generosity of the cosmos, offering us glimpses of its deepest past through whispers of ancient light. And yet the CMB, for all its precision, does not resolve the tension, it sharpens it. The early universe tells us one story, the present tells us another. Between them lies a gap that refuses to close. To bridge it, we must treat the CMB as the baby picture it is. A glimpse of the beginning, but not the whole tale. To complete the story, we must trace how expansion evolved across billions of years, comparing then with now. And that leads us to the grandest map of all, the cosmic microwave background map. When scientists first mapped the CMB in detail, it was like unrolling a parchment written in light. The map revealed patches, ripples, and patterns across the entire sky. Each variation in temperature, no larger than a few millionths of a degree, held meaning. They showed how matter clumped, how sound waves rippled through the early plasma, and how the universe expanded in its infancy. The cosmic microwave background map is, in a sense, the universe's birth certificate, signed in light, stamped with the physics of creation itself. This map became the cornerstone of modern cosmology. It confirmed the Big Bang, revealed the ratio of dark matter to normal matter, and pointed to the presence of dark energy as the dominant force shaping the future. It showed us the flatness of space, the distribution of primordial fluctuations, the fingerprints of inflation in the earliest moments. From this single image, entire cosmological models were built, models that predicted not only how the universe began, but how it should evolve across billions of years. It was a triumph of science and imagination combined. Yet, as precise as the CMB map is, it deepened the conflict with local measurements. According to its predictions, the expansion rate today should be slower than what Cepheids and supernovae suggest. The map and the candles tell two different truths, each consistent within its own method, but inconsistent with each other. The more accurate the map, the sharper the contradiction. It is as though the baby picture and the adult portrait do not match, both authentic, both undeniable, yet mismatched in ways that demand explanation. For astronomers, this mismatch is both frustrating and thrilling. Frustrating because it refuses neatness, thrilling because it hints at something extraordinary. Perhaps new physics operated in the early universe, early dark energy, exotic particles or dimensions beyond our sight, or perhaps expansion itself evolves in ways we cannot yet grasp. The map does not answer these questions, it only asks them louder, insistent in its quiet detail. Every pixel of the CMB map is a whisper from the past, calling us to reimagine the present. And so, the cosmic microwave background map stands as both guide and challenge. It anchors our cosmology, yet unsettles it. It confirms the Big Bang, yet destabilizes our understanding of today's expansion. It is a reminder that science is not about closure, but about questions that deepen with precision.